Y si hay gente conectada por YouTube.
Bueno, buenas tardes. Nos encontramos de nuevo en el tercer día del primer encuentro de Lingüística Experimental. Ahora tenemos el taller Pupilometría y Análisis de Datos en R por el doctor Camilo Rodríguez Ronderos.
Bueno, gracias. Aplausos, un poco. Listo. A ver. Acá. Muy bien. Están maximizados. Sí. Ok. Bueno, pues muchas gracias. Hola de nuevo. Entonces, vamos a empezar un mini workshop, por así decirlo, de 2 días, donde la idea es darles como una especie de introducción muy veloz y muy compacta al uso de la pupilometría para investigar fenómenos de la lengua. Entonces, lo que primero, antes de empezar, o sea, lo que me gustaría como saber un poco de cosas preliminares sobre ustedes, como tipo, ¿cuántas personas acá han usado antes R? Ok. Eh, ¿Cuántas personas acá han ya hecho como un análisis entero de un experimento? Ok, ok. ¿Cuántos de ustedes tienen planeado de pronto usar pipilometría para un experimento? Ok, bien. O sea, si es algo que quieren hacer y o sea, y están como a punto de... Bien, bien, entonces esto sí tiene sentido. Entonces lo que voy a hacer es, hoy ahora darles una introducción general sobre la pupilometría, pero también como hablando de aspectos del diseño experimental que son súper, súper importantes. Y tratar como de pues, tener una discusión abierta. También me pueden interrumpir cuando quieran. O sea, la idea es que sea un poco más como estilo taller y no como una cátedra. Y, y para el día de hoy no necesitan como tener sus computadores ni nada, si quieren tomar notas de eso, pero hoy no vamos a usar R. Y mañana la idea es, yo les voy a traer un dataset mío de un experimento súper sencillo que por eso me parece bastante bueno, y son pocos participantes, es datos piloto, y los voy a llevar como paso por paso, cómo hacer el preprocesamiento, procesamiento de los datos, visualización y análisis de todo el experimento. Pero entonces como que lo que no vamos a hacer es coger el eye tracker y programar el experimento directamente ahí, porque eso llevaría pues mucho más tiempo y esa parte es, para el experimento de volumetría es ligeramente trivial, o sea, en comparación con otro tipo de paradigmas como el Visual World, donde es mucho más complejo y sí requiere más como atención. Igual eso espero que sea un poco como evidente después del día de hoy, como que en realidad estos experimentos no son difíciles de programar. Mientras que si ya han programado algún tipo de experimento, añadirle como pupilometría no va a ser complicado. O sea, son otras cosas que son más difíciles de controlar. Y en todo caso, como igual realmente es muy poco tiempo, entonces no los voy a bombardear con información, que no sé si ustedes han atendido como mini workshops antes, pero uno sale como a veces más confundido que antes, porque es demasiada información. Entonces vamos a tratar de hacer como pocas cosas, pero como distribuidas en una cantidad de tiempo decente y al mismo tiempo sí, y al mismo tiempo también, o sea, les quiero decir que si quieren programar un experimento por mentira, cuando estén haciendo sus propios experimentos, con muchísimo gusto me pueden escribir, así sea en un mes, así sea en 6 meses, o en un año, lo que sea, y yo les ayudo con lo que necesiten. O sea, eso eh, para todos ustedes que sepan, porque igual siempre van a haber cosas donde detalles del experimento en particular que no puedo cubrir, o sea, voy a tratar de ser como lo más general posible, pero siempre hay particularidades para experimentos y condiciones y diseños que toca ver como case by case, o sea, no se puede hacer como todo al mismo tiempo. Pero bueno, entonces vamos a empezar. Voy a cambiar a inglés, porque esto va a ser puro Spanglish. Si quieren preguntarme en inglés o en español, todo bien. Em, em, eh, Sigo en español un rato hasta ver cómo nos va. Igual, bueno, yo ya me presenté hace 2 días, y ya saben un poco más de mí, pero es importante como que que decirles que yo soy lingüista experimental, mi formación es en lingüística experimental, es diseño estadístico, diseño de experimentos, pero soy fundamentalmente lingüista, o sea, yo no soy biólogo ni neurocientífico, Y mi interés en pupilometría está en función de usar este método para testear teorías lingüísticas o teorías de la ciencia cognitiva. O sea, yo no soy como un fetichista del cerebro, sino a mí lo que me interesa es aprender cosas sobre la cognición. Entonces, lo que les voy a enseñar, o lo que vamos a tratar de discutir estos días es cómo usar la pupilometría para testear hipótesis. O sea, hypothesis testing es como lo que a mí realmente más me interesa. Y si ustedes son lingüistas experimentales, supongo que a ustedes también es lo que más les interesa, testear hipótesis. Em, Aunque yo ahora trabajo pues de profesor de lingüística, por los últimos 4 años yo hice el postdoctorado en Oslo y yo tenía dos puestos en Oslo. Uno era de postdoctorado en lingüística y filosofía y el otro era de Technical Advisor for the iHub Network on Eye Tracking and Peopleometry, donde yo básicamente pues, ayudaba a mis colegas y a los estudiantes a diseñar los experimentos y varios workshops sobre tanto eye tracking como pupilometría. Entonces, esto es algo que pues he hecho, llevo haciendo ya pues, algunos años, también desde mi doctorado, también trabajando con eye tracking y pupilometría. Y bueno, lo que les decía, mi trabajo, del que ya pues vieron un par de experimentos y un par de trabajos, se trata de confirmatory hypothesis testing. O forzar a las teorías de la lingüística o de la ciencia cognitiva a que nos den predicciones que podemos testear. Y para eso la pupilometría es súper útil. Ok. So, voy a cambiar en inglés porque ya me está dando un poco de cognitive load hablando en español. ¿No? All right. So what I want to do in this workshop is to provide a basic idea of the why and how of people-centered experience for confirmatory hypothesis. So we will do the following three things in the next 2 days. First, discuss the motivation for why you want to use pupilometry. So why this and not other methods, right? Um, Discussing the most important things to consider when setting up a link hypothesis. This will become evident throughout the day. But one big problem with pupilometry is that the interpretation of the pupil record is ambiguous. You can have multiple interpretations, so you need to pay a lot of attention to how you construct your experiments so that the interpretation that you want to have is actually licensed by the experiment. And we'll go briefly through the design and mostly the pre-processing analysis of a simple pupilometry experiment. So for this, tomorrow, I will send you, when we start, I will send you, I'll put up a link, and then from that link, you can download the data and the analysis script. So if you want to, you don't have to install R in RStudio, but if you want to do that, and play along on your computer, that will be very helpful for you. If you don't know how to use R, if you've never used it, don't worry. Like I'm also just going to go through it on the screen here. So it's easier to learn if you're doing it on your own computer and stuff. And I will say this again tomorrow, but the data that I'm going to be sharing with you is unpublished, is pilot data. So please do not share it with anyone. We're also not going to do a YouTube transmission tomorrow. Sorry, people on YouTube, because I don't trust you. I don't know who you are. So sorry. But I hope you forgive me. And that's what we're going to do tomorrow. Okay, so yes. So today we'll discuss this thing. Today and tomorrow we'll continue discussing how to set up a link hypothesis, and the actual core of the pupilometry analysis will be tomorrow. So another couple of things to get out of the way. A lot of what I'm going to do today is based on the work of Drew McLaughlin, who is a postdoc at the BCDL, the Bass Center for the Study of Language and Cognition in San Sebastian. Her work is amazing. Please read her papers. And she's also done a lot of teaching on pupilometry, and I'm going to be basing a lot of these things on her work. And also critically on the work of Sebastian Mator, Sebastian is basically the world expert on cognitive pupilometry. What I'll do tomorrow as well is when I send you a link to download the script and the data, I will also send you a bundle of papers that you can read that are great. So a lot of them are from these two people. They're kind of introductory. All the papers that I will mention throughout the day, I'll send them all to you, so you can have all this at home. And then in terms of analysis, if you've used R before, you probably know this. A lot of the work that is required to use R properly involves downloading additional packages. These packages are usually made by like random scientists, right? And who put a lot of work and effort into doing these things, and they don't get that much credit. And then the one that I'm going to be using tomorrow is this really, really good package called Gaze-R that also has great documentation. So, and there's an accompanying paper that you can read and code that you can download. And this was done by the people here, Jason Geller, supervised by, Dan Merman and Tristan Marr and Matthew Wynn. And this is really amazing work that they did to make all of our lives a lot easier. So we're going to be using their package tomorrow. But there's a bunch of other R packages that are also good for analyzing people data. But this one will be particularly good for you guys because it's the one that is most compatible with different types of eye trackers. So there's packages that I think are a little bit better, but maybe only work with data from the SR Research iLink eye tracker. So whereas the ones that they made is compatible across platforms. So basically all you need is any machine that spits out a data set, one data set per participant that has a column that tracks the pupil, basically. And I think, as I've heard, you guys have the Tobii eye tracker that does just that. So anyway, so that's what we're going to be using tomorrow. Okay, is there anything that you guys want to ask or say before we get started? No, okay, great. So I'll start with a very basic observation. This is an eye. This is presumably a human eye, right? And in a human eye, the pupil is the kind of the empty hole. I'm just using non-technical terms. The empty hole within the iris that allows light to pass through the lens back to the retina. The iris is the colored bit, right? And then basically, you can also think of it metaphorically as the pupil being the gate to the retina, right? So the retina is the back of the eye. If I do this, can you see my mouse? Yeah. The retina is the back of the eye. The part closest to the optic nerve is where where the equal concentration of kind of like rods and cones that kind of sends the electric impulse to the optic nerve and allows you to see stuff. So the retina is really important for receiving light, and the pupil has a really important function to regulate the amount of light that the retina obtains, right? So it has a dual role of both protecting it from too much light, because we don't want to burn our retinas, right? Staring into the sun. But it also wants to maximize the amount of light that you're getting when you're in an environment that has low light conditions. So when you enter a room and the room is dark, your pupil will do some adjusting so that your retina can get in as much light as possible. These are the two main functions that the pupil serves, right? And this is done by two movements of the muscles in the iris that are called constriction and dilation. So the muscle tissue in the iris changes the diameter of the pupil. The muscle closest to the pupil is called the sphincter pupillae, and it moves in this kind of rotating fashion, right? And it constricts the pupil, right? It makes it smaller. And the muscle tissue on the outer part of the iris pushes outwards to dilate it. So these are the muscles that are responsible for constriction and dilation. These are two separate types of muscular movement in the iris. So and it all looks a little bit like this, right? So even though it looks like kind of like the same kind of movement, it's the constriction and dilation are actually controlled by two different processes, and they're associated also with two different parts of the nervous system, two different autonomous nervous systems, which we will talk about a little bit. Okay, so what causes changes in pupil size, right? So as I mentioned before, the main function of the pupil is to regulate light, and kind of it would make sense then, or I hope it makes sense that the main move this out of the way. The main thing that causes the pupil, that changes the size of the pupil, is light regulation. This is known as the pupil light reflex. So light, as this is illustrated by Aaron in Sebastian Mato's 2018 paper, is the main determinant of pupil size. And you can basically think about it, and when there's an increase in light in the room, this activates your parasympathetic autonomous nervous system, which is the one that is known as kind of like the rest and digest autonomous system, or you can think about it as the one that's responsible for homeostasis. So it regulates kind of like the bodily functions that maintain the body in kind of a stable condition. And it regulates constriction. And this also kind of makes sense if you think about how your pupils are relatively small when they're in a resting state. So in a resting state, we want to have like small pupils to let in as little light as possible. So you're protecting the retina, and this is generally regulated by parasympathetic activity. On the other hand, when there's a decrease in light, this is usually associated with sympathetic activity or activity in the sympathetic autonomous nervous system. This autonomous nervous system is, sorry, not autonomous, autonomic nervous system is the one that's typically associated with arousal, wakefulness, or the so-called fight or flight response. And the dilation pathway, it actually starts at the locus coeruleus, which is Latin for the blue point, which is this part in our brainstem that produces neuroepinephrine or neuroadrenaline, which is why often pupil dilation is used as an index for activity in the locus coeruleus. So it's actually dilation of the pupil is kind of a direct measure of neurological activity and the production of neuroepinephrine in the locus coeruleus. So it is, in a sense, yeah, a direct neurological measure. This is why pupillometry is considered to be not the same way as eye tracking or as eye movements are. So eye movements are kind of under direct control, sometimes not. Whereas we don't really control. We have no direct control over our pupil dilation, and it is really an index of neurological activity. Right. So to show you what light does to your pupil, this is a graph from this really good Mattel paper from 2018. So this is actually data that Sebastian collected on himself. So he put a camera on his eye, and then he exposes his eyes to light, to red light and to blue light, and he measured the change in the pupillary in his baseline pupil size. And this is the graph that's in the paper. Now this graph shows us two things that are super interesting, and it's really important to pay attention to this. First one, if one over here is the resting state of the pupil, this is the line here, and numbers below this show a reduction in pupil size, and numbers above it would be an increase in pupil size. So look at what happens when he starts exposing his eye to blue light and to red light. There's a huge decrease in pupil size. So it goes from 1 to 0.4. That's basically a 60% decrease in pupil size just by showing a light from a computer screen. And then the other really important thing that this graph shows is that the different types of light make a different type of change over time in how the pupil dilates. So red light kind of bounces back more quickly, whereas blue light has sustained constriction in pupil size. Now, why am I emphasizing this? Because when you construct your experiments, you have to think about the fact that changes in light will have a dramatic impact on the changes in pupil size. This is something that we're going to have to consider take very, very seriously when you're making your own pupillometry experiments. Right. The second thing is a so-called pupil near response, which basically your pupil dilates and change and constricts when you go from looking at faraway objects to close by objects. So Mattel says that this is actually probably the least understood of all pupil responses. It's kind of unclear why this happens, and he writes in this paper that there's not that much research on it. This is a paper from 2018. I don't know if there's been more research on this since then. To illustrate this, he did the same experiment on himself, right? He had 2 cans of Coke and first started looking at the one that is far away, and then switches to looking at the one that's close by. And there's a decrease in pupil size from 1.0 to 0.7, so about 30% change in pupil size. That's huge. And then as soon as he goes back to looking at the one that's far away, very quickly the pupil dilates again. So the way that you focus what you're looking at will have a huge impact on pupil size. Another thing that we're going to have to consider. Very, very important thing to consider. Right. There's another type of pupillary responses that I'm going to call, these are kind of like what I call fake pupillary responses, because they're not really affecting how your pupil dilates, but it affects how the measurement how the dilation of pupil is measured, and these are saccadic eye movements, right? So what you see here is a grid of a person who is looking at the different corners of a computer screen. And what do you guys notice about the pupil? Any thoughts? What is happening to the pupil in these different images?
Changes in size.
Yes. How so? Or what do you see? What do you see changing?
The angle.
Right. Yeah. So in here, let's assume that this is a somewhat perfect circle in the middle when the person is looking straight to the middle, right? If they're looking to the top like this, yeah, it actually goes down, and it looks like a squished oval, right? And if you're looking to the sides, it looks like a squished oval in the other direction. So it creates the illusion, depending on where your eye tracker is placed, that there's differences in the size of your pupil. So this is called the pupil foreshortening error. So looking on the different screens affects the measurements because an oval shape tends to have a smaller diameter than a circle shape. Everything else being equal. Does that make sense? Right.
It also kind of gets like covered.
Yeah. That's a really good point, and that is going to be really important for blinking, which we're going to be talking a bunch about. There are people who say that this can be corrected, and there are eye trackers and fancy measurements that solve this problem using a 3D model of the eye. So basically, if you have an accurate enough model of what your eye looks like, and the position of the camera, you can kind of correct this. But obviously, if you can correct something, I think it's better to prevent something from happening than correct it once it has happened. So this is going to be important for how you construct the experiments. Right. So how do we measure pupil dilation? This is a very basic question. We measure it using an eye tracker. This is normally how it goes, right? There's different types of eye trackers. I want to mention two cases, which are kind of two very extreme cases of two very different types of eye trackers. And then there's a bunch of cases in the middle, right? And then the one that you have, as far as I understand, is closer to this one, but it's the Toby, what's the
Spectrum.
Spectrum, yeah. So this will apply somewhat to the Toby spectrum, but I'll talk about the differences, and we can also talk more about these differences. So I'll talk about the ILING 1000 because it is very likely that if you go to another lab, that you will hear about this, or that you will read papers where the data was collected with this eye tracker. It's kind of considered the gold standard in eye tracking. There's two ways of using it, either head free or head fixed. The head fixed is the most common one. So this is the most accurate eye tracker. They can think of its samples at 1000 hertz per second. So you get 1000 images of the eye per second. It's a bit of overkill, to be honest. And it has multiple advantages. So it's very high accuracy and experimental control. It's super user friendly. It comes with like software that you can use. They answer a lot of questions from the company when you have problems. The tech support is really, really great. The main disadvantages with this, first of all, it's not very ecologically valid. If you're putting people, on a chin rest and they're kind of like fixated there, and you have to kind of have all this experimental control. Sitting, staring at a computer, sometimes not the most ideal way of going about this. It's extremely expensive. And by extremely expensive, I mean like upwards of 80,000 euros, right? So this is pretty much unaffordable if you're, unless you're in a rich institution. So we would ideally want to look for alternatives. What I'm going to talk about now is also the extreme case in the other direction. So these are the neon glasses made by this company Pupil Labs, the startup. This is my friend and collaborator Dale, who's modeling the glasses for us. So these glasses are extremely affordable. How they work is basically there's these two little cameras that are embedded into the frame of the glasses. And this is called near eye technology, so to measure the eye from a very, very close point. And overall, they cost about 5,000 euros. It's still a lot of money, but you can still. I mean, it's not 80,000. You know, like they're extremely accurate when it comes to measuring pupil diameter. So because of the near eye technology, basically you don't have the problem of like distance to something. So you have less of the type of errors that are generated by like an eye tracker. And you have this kind of really close camera to the eye. In fact, there's a paper by a group of psycholinguists in Stuttgart who compared in a battery of different tasks the performance of the neon glasses with that of the iLink 1000. And for pupils specifically, for pupil measurements, there was no significant difference between the measurements produced by this one and this one. So I'm also attaching this paper in the bundle of papers that I'm sending you. So it's a serious option to consider. And it's also super portable. So they're just glasses. You can take them anywhere. They have high ecological validity. What I mean by this is you can have people talking to each other, or you can just have someone talking naturally. And maybe, yeah.
Can you wear them on top of glasses?
No, you cannot. But they come with different settings. So they come with like different lenses with different measurements. So basically you can have, if someone wears glasses like me, you can ask like what their prescription is, and then you can kind of like, you know, like an Oculus, like just kind of change them and put them. You can wear them on top of contact lenses, and it doesn't change the measurement. Yeah. The disadvantages is that they're somewhat less user-friendly. So things like the iLink 1000 and the Tobii, because they want to sell the whole package, they put a lot of effort and money into this kind of proprietary softwares as well that are supposedly easier to use. I don't particularly like using the Tobii software, but it's like they come with a lot of instructions because they build them mostly also for commercial usages, specifically the Tobii. They sell them mostly, their biggest customers are like companies who want to do like market research. And so they have like specific software. So with the neon glasses, you don't have this kind of out of the box software. There's no like real tech support for it. There's a big community online who uses them. So you can ask people questions on forums. And you can use ideally also open source softwares. So stuff like Open Sesame to program your experiments. So it's a little bit of a slightly steeper learning curve because you have to do a bit of hacks to learn how to do it. This is changing though. So because they're becoming more and more popular, there's more kind of accessible options. But the fact that it's less user-friendly also means that everything is free. So basically you buy the glasses and you can use free software to program the experiment, free software to analyze the data. And this makes it really, really appealing when you're not, you know, fucking MIT or something. I would say that it's probably limited to pupilometry. This is not really true. I mean, it tracks your eye movements, and people use it for eye tracking. What I mean specifically is that I find the eye tracking to be somewhat coarse-grained. So you cannot do an eye tracking during reading experiment. For example, the experiments that Jesse was presenting earlier, you couldn't really do these with these glasses. You could probably do an eye tracking experiment where you have like maybe two objects, you know, that are very far away from each other, and you want to see which of the two the person is looking at. Something like this. But that is also that is a little bit tricky. I would probably recommend using them for pupilometry mostly. But anyway, if you think about where the Tobii falls between these two, it's somewhere in the middle, right? It doesn't sample at 1,000 hertz. It samples, I think, at 250 or 200. The one you have samples at 2,000 hertz. That is crazy. Yeah. That is crazy. Yeah, I'll have to look at it later. Right. But anyway, as you will see in a little bit, all this is crazy overkill, and you don't really need more than 200 hertz for tracking the changes in pupil size, or for eye tracking for that matter. But okay, let's ask some more fundamental questions. Why should we care about pupil dilation? Does anyone have any answers for this already? Why are we here? Why does this matter? Right. So the reason why I care about pupil dilation, and why I think that you two should care about this, is because there's a well-established systematic relationship between pupil diameter and cognitive load. So more cognitive load is typically associated with more pupil dilation. Small pupils are associated, like I said, with resting states, because this is controlled by the parasympathetic nervous system that kind of wants you to be in this resting state with your pupil is relatively small. It is typically indicative of reduced cognitive load or like baseline state cognitive load. Larger pupils, as I mentioned, are usually the products or brought about by a rush of norepinephrine, seeing as it is regulated by the sympathetic autonomic nervous system, and it's associated with this kind of state of alert that is typically indicative of more cognitive load. Importantly, this is something that you have to kind of also really be mindful of, and we will talk about it some more, is that the response time of like a release of norepinephrine and the dilation of your pupil is about 1,000 milliseconds after a stimulus is produced. So this paper that I'm referencing here, I'm also attaching it, the Hooks and Layfeld paper. This is like the response to like a sound, basically. So the most overt stimulus that you can think of, it'll take about 1,000 milliseconds to reach its peak in terms of what the cognitive process is on your pupils. So you want to construct experiments that account for this lag of 1 second. Okay. Are there any questions so far? Real good. Okay. Right. So I want to show you now what is the standard pupillometry results graph. Because I don't know how many times you've seen graphs like this, but this will be important for when you look at your own data. So what you usually have is on this axis we have the change in diameter, so the pupil diameter. This is usually measured in abstract units. We usually don't care about the actual unit that is being used. This is because to measure it precisely in millimeters, which some people do, you need to have the distance between the eye and the camera, and sometimes you don't have that, right? So what you get, the column that you get from the data will actually just be in random units measured by whatever the eye tracker wants to be measured. It's still super accurate, right? It's relative to itself, but it's just not in any kind of tangible units. You can convert it either to millimeters by measuring the distance to the eye tracker, or you can convert it to, you can standardize it like using like z-scores. I don't do either of these things. I just always keep it in abstract units. And I think this is fine also. But yeah, you can kind of decide that on your own. Right. So what we usually have at the 0 point, and before that, sometimes you also want to plot like negative numbers. You will have your baseline pupil diameter. So basically, what is the size of your pupil before your critical event? You usually want to have this time locked to some form of relevant onset to the stimulus. So this could be the beginning of your trial, if this is what you care about, or this could be the beginning of a specific word that you care about in a sentence. This will be important for how you analyze the data, right? Because you want to basically, when you get the data, you want to time lock it to the beginning of the relevant word that you have. So what this involves normally when you design an experiment, this is the same for eye tracking, is that you want to have let's say you have a sentence like, for example, I just ran a pupillometry experiment where the sentence is the line that Jasmine drew was straight, and I care about how they process the word straight, and it's at the end of the sentence. So I measured in milliseconds at what point during the sentence does the word start, and then you add that to like your column and then your data set, and then you rearrange the measurements of the eye tracker so that everything starts at the beginning of that word that you care about. This is called time locking. I don't know if this is obvious to you guys. I'm just kind of like going through the whole thing, and yeah. So yes, so that's what you would want to do. That's where you would have the 0 normally, and then you normally have this kind of curve that looks a little bit like this. It'll obviously change, right? But you have basically a continued dilation as a response to the stimulus. It reaches a peak, and then it'll revert back to a baseline. And this peak will be reached at around or at the earliest after a second, but it's usually around a second. That's the kind of the pupillary, cognitive pupillary response. The bigger this curve is, right, the more cognitive load, the smaller it is, you have less cognitive load. Now, there's a lot of things that can change here, right? You probably notice this. This is not just about size or like, so there's many ways in which you can quantify the differences between these lines. But maybe you guys have an idea of what I'm talking about. No?
Isn't it that, I don't know, I was thinking, what if the phenomenon that you're studying is not reflected in the pupil, and there's no response in the sense that probably you're expecting. There's no peak, or there is a peak, but it's actually very, very low. Probably that's
Yeah, that could happen. I mean, but ideally you want to have a control condition, right? So you're measuring one phenomenon against another one. And then you would see which of the two is associated with the most cognitive load via more pupil dilation.
I
Right?
was thinking, for example, in terms of one single word.
Yeah.
What if the PD does not really respond to that field?
I mean, so it will respond in some sense because you are processing it. So there's mental, we assume that there's mental activity, that you are integrating it, you're building syntactic structure, you're retrieving the lexical items and
It
so on.
was, but not in terms of what probably is expected.
Yeah.
In terms of the size of the
But I think you have to remember that this is a relative measure. So let's say you have to compare one thing to another,
Yeah.
right? If you're looking just at one thing,
No.
you can't really draw. So you would basically, let's say, okay, so this experiment that I was telling you about where I gave participants the sentence, the line that Jasmine drew was straight. Are we locked in? Oh no. We have to spend the night here. So yeah, so the experiment that I had, the line that Jasmine drew was straight, and then I showed them two pictures before that, one in which the line was squiggly and one in which the line was perfectly straight. So that you're hearing the same word, but you're comparing it as how it's integrated with context in two different cases. One in which you assume a kind of a precise, and one in which is kind of an approximative interpretation. But yeah, but we'll get to concrete examples. What I wanted to talk about was that yes, so exactly. So you could think of it as like, what is the maximum peak? So you can have identical curves that change in the same way, just that one goes higher than the other. Or you could have changes in which one curve would go. Can I draw actually on this? Can I put that? Wait. Oh yeah, I can draw on this. You could have a line that goes like this, right? So that it takes longer to reach a peak, and then the peak is smaller. Or it could take longer and then maybe reach the same peak as the other one, but just be overall, but the decrease would also be longer. There's all sorts of different shapes of curves that you can have. And this is going to be really important to think about when you're doing the data analysis. So what is it that you care about? And what I'm going to show you, because it's, so there's no method that I think is perfect, but tomorrow for the analysis, we're going to be looking at a method that's called growth curve analysis, in which you look at not only linear change, which is what the linear regression model does, like whether the curves, draw again, whether one of them is like a line that is, man, I'm so bad at this. How do I, there you go. Okay. Can I make the curve? Here we go. Yeah. So you could have like in a linear model, you could say like one condition is like this, like increases linearly like that, and one condition increases like that. So you would have like a difference in the linear component of the curve. But then you can also have a change in the quadratic component, which is like the shape of the curve, like this, or in the cubic component. So it could be like one curve goes like this, and the other one goes only like this. So there's all sorts of different ways, mathematical ways, in which you can compare curves one to another. And so we're gonna be using this, but we'll talk about it tomorrow. But you can also measure, for example, just kind of like and I'll show you some examples of people who have done this, aggregate across the entirety of the time, and then have a bar graph that shows you, oh, overall, there's more pupil dilation in this one relative to the other. So, but then you would ignore the kind of temporal component. Anyway, I'm rambling a bit now, I think. This will become clear when we look at some examples, I think. But yeah, interrupt me at any time if you're like, what the hell are you saying? I don't understand anything. Please do. Right, so the example that I have here is one from the experiment that I'm going to show you tomorrow. So 2 days ago, I told you a bit about my work on expressive adjectives, where I'm interested in things like, words like fucking. And the experiment that I'm going to show you tomorrow is a very simple pupilometry experiment that I ran, where participants hear sentences like, the fucking keys are in the apartment, after they read a short context, something like, John rushed to the airport, and then he said, the fucking keys are in the apartment, versus the apartment keys are, no, not the neighbor's keys are in the apartment. So basically, you have a kind of like an expressive adjective compared to either a compound word or a descriptive adjective. So basically, and what we're investigating here is the so-called taboo effect, that words like fucking should elicit more cognitive load because you experience some sort of shock about like, oh, this is kind of the violation of some social norm. And also because you have to be thinking about the speaker's mental states. You have to be thinking about like, oh, that person is upset about the fact that he left his keys in the apartment. So yeah, so it's very, very simple in the sense that you just have two conditions. So comparing the word fucking to the word neighbors. And then we would expect basically expressive adjectives to elicit higher pupil dilation. And the data is timed up to the beginning of the adjective. And the idea is that the more dilation we find, it'll be more challenging to integrate with the kind of like the sentence and kind of like what the person is, the kind of mental activity going on in the comprehender versus if the curve is kind of smaller, which we predict to happen for the descriptive adjectives. So that's kind of like what we're going to be looking at tomorrow. All right, does that make sense so far? Mm-hmm. Yeah, are we all on board? Okay, great. So what I want to show you now is talk about some key findings regarding the evoked pupil response. This is going to be important because these are basically things that you will need to cite in your first pupilometry paper. So this is what will anchor, and I'll also add all these papers to the folder that I'll give you tomorrow. So these are kind of the most important fundamental findings, both in cognitive science and then in the language sciences. So a really, really basic one. So, because I mean, I'm saying this because I don't know how much you guys know about pupilometry already. So if this is too obvious, I'm sorry. Okay. So Daniel Kahneman, who passed away recently, I think last year, and also first psychologist to win the Nobel Prize. He started his career in the 60s with actually doing pupilometry. So this was something that was big in the 60s and then kind of went dormant and was kind of revived in the late 90s, 2000s. But then they discovered this very fundamental finding that there is a relationship between memory load and pupil dilation. So they gave participants strings of digits that varied in length. So something like 8, 87, 875, 8,759. And they just asked people to remember them and then to say them back. They had to kind of, yeah, it's a recall, a so-called recall experiment. And importantly, they had a camera that was pointed to the eye of the participant via some mirrors. So this is like doing experiments in the 60s must have been crazy. Basically, it's a bunch of mirrors and a camera, and then the participant had a box, and then there was a person taking a picture with a physical camera as quickly as possible. So they took a picture, one picture per eye, one ppicture per second of their eyes to see how the pupil dilation would change. And then they measured by hand. So they printed out the picture. They had to take the picture developed to Kodak or whatever, and then by hand measure with a ruler how big the pupil is, and I mean very, very cumbersome process. And the 60s, yeah. Yeah, they probably had some research assistant hidden away in a basement doing this. Yeah, exactly. And then this is their key finding. So basically, this is time measured in seconds. This is from the onset of when they started, right after they told the participants to start remembering, right? So they're like, oh, we're going to tell you this number, you have to remember it. And then there was a pause, and here's when they have to start saying it back, right? So you see that before they have to start saying it back, by far the largest pupil dilation is elicited by when they have to remember 7 digits. And then you find this really, really neat pattern as a function of the number of digits that they have to remember, which is it's pretty wild. Like, you rarely find things this clear in cognitive science, like these really, really clear results. To the point that Daniel Kahneman said in an interview that the effect sizes were so big that he could see it. So he could see people's eyes, the pupil dilating. And this is a very, very appealing thing about using pupillometry, that you usually have really big effect sizes, right? So effect sizes that are visible by the naked eye, this is stuff like Cohen's d of 0.7. This is we're talking about the realm of effect sizes of like men are taller than women. This kind of effect size that is very visible with the naked eye, that you don't need huge sample sizes to kind of come to these conclusions. So obviously, not every phenomenon that you're going to investigate is as clear as remembering digits, but this is a huge advantage of the methods that we need to have, where the effect sizes are very small. Right. So another really critical finding, and another group that studied. So there were 2 groups in the 60s that studied pupil dilation. There's the Kahneman and Beatty group, and then there's the Hess and Polt group. And what they did was they showed that pupil diameter is associated with arousal in ways that are person specific, which is also indicative of cognitive processes. So it's not just that people just dilate all the time, right? So, and we know this because they ran an experiment where they showed men and women pictures of either naked men or naked women, or babies and mothers holding the baby, right? And the results are also quite like strong in terms of the effect sizes that they found. So when they showed men pictures of babies, their pupils didn't dilate at all, whereas women's pupils dilated quite a lot. When they showed, you find a similar effect for a mother holding a baby. When they showed men or women pictures of naked men, men's pupils dilated a bit more, but women's pupils dilated a lot more. And the effect flipped when you showed them pictures of naked women. So men's pupils dilated a lot and women's didn't dilate as much. And when you show them landscapes, their pupils didn't dilate particularly much. So they also replicated this finding a couple years later with people with different sexual preferences, and it matched the sexual preference of the participants. So basically, men were attracted to men, their pupils dilated when they saw pictures of naked men, and the reverse with women. So what they argue is that this shows that we're talking about specific types of cognitive activity that are related to arousal, which again is directly related to the fact that this is regulated by our fight or fight responses that produce more neuroepinephrine, and therefore leading our pupils to dilate when we're more aroused, or when there's more cognitive activity involved. Does that make sense so far? Right. Another paper that I'm attaching to this that I'll send you tomorrow, that I strongly advise you to read. It's just a summary paper by Beatty in 1982 that's wanted to summarize the state of the art of pupillometry in 1982. He then wrote another one in 2000 to kind of like see what we had learned. And he has this graph that's quite handy. It's basically, these are just like kind of and measured in millimeters. And I don't think this is like super accurate, but roughly he's trying to show the type of effect sizes that you find for these different cognitive domains. So for memory, language, reasoning, and perception. And you see that for reasoning, you have really big effect sizes. This is also from the Beatty and Kahneman group. Basically, when you ask people to multiply stuff, just remembering a number versus making an easy multiplication is associated with huge changes in pupil size. And the harder the multiplication, the more your pupil dilates. So the more you have to the more cognitive activity, the more you have to, the more your pupil dilates. The memory ones, you find these are kind of like linear. So these seem to work kind of more on a log scale in terms of how much you realize, but these were the remembering things just kind of very linear. And with language, what he talked about, like, yeah, remembering, matching words hard, easy, reasoning grammatically, these are psychologists, so these are not really linguistically relevant terms. But the idea is that basically the harder the mental process is, the more your pupil is going to die. You can count on that. It's a very strong, robust finding across domains in cognition. All right, so there has been some language specific findings. What time did we start? Did we start at 12:30?
Yeah.
Okay. Okay, so we have until 2 or until 2:30. 2:30. Okay, so we have another hour. Okay, let's see. Okay. Okay, so in terms of language, the first finding is this by Justin Carpenter, who you might know also from, eye tracking results and the what's it called, the eye-mind hypothesis. So what Justin Carpenter did is they showed people object relative clauses versus subject relative clauses, center embedded subject relative clauses versus center embedded object relative clauses, and they found that the object relative clauses are associated with more pupil dilation. So let me think of an example. It's something like what were the examples? Do I have the paper here somewhere? Here's the paper. Yeah, here we go. So they reported that the senator attacked admitted the error. That's an object embedded clause. Versus the reporter that attacked the senator admitted the error. And the first type of sentence, the reporter that the senator attacked, is more elicited more pupil dilation. So that's when they start saying, like, okay, their conclusion, which you can see here, is that the more complex sentence also, we propose that the pupillary response is an indicator of how intensely the processing system is operating. And roughly speaking, we still kind of hold that same kind of linking hypothesis. There's been a bunch of additional findings in the syntactic domain, testing different types of syntactic constructions, different types of constructions and how they interact with phonology, with prosody. This is also actually what Jesse Harris has done. He's probably more qualified to be teaching this workshop than I am. But in terms of findings that I find particularly interesting, because I work in pragmatics, are these ones by Tromp et al. This is from the Max Planck Institute. This is Tromp and Anchemaya. And what they did was they measured the pupil dilation associated with processing sentences like it's very cold in here, embedded in context in which it was clear that the person was using it as an indirect speech act. So when the person was saying, like, when it should be interpreted as, can you please close the window, there was more pupil dilation than when it was just an assertion. So I think this is great because it's basically, the claim that they make is that, well, the additional inferences that you're deriving are associated with more pupil dilation. And this is effectively a very good working hypothesis if you're working on pragmatics. So if you're interested in doing pragmatic experiments with pupilometry, this is the paper that you want to cite, right? There's also Mon et al. 2021. This is a JML paper who looked at metaphors and found more pupil dilation in metaphors even when they were conventional. So also claiming that there's kind of some additional inferential meaning that is being retrieved, or maybe emotional meaning. And so basically you're getting more out of what you're processing. I have done some work on this also on metaphors and as part of my PhD. Also showing that processing metaphors is associated with more pupil dilation than literal equivalence. Right, so that's basically.
So, for example, in an experiment where you have kids, you're testing whether they process the metaphor or not. If they don't, you should expect you will predict that there is no more dilation versus a literal interpretation of something.
If they're not processing the metaphor.
If they're not processing. And versus adults processing the metaphor with versus something literal, then you will expect more dilation in the first instance. right?
I think that depends on how you construct the experiment. So, for example, if you have comprehension questions afterwards,
Because the one that you had, right? The kids and the picture. La mujer con patas de gallina, something like that. And they were showing pictures where there was a woman
Yeah.
with literally
chicken
patas
legs,
de gallina.
yeah. Or
Kids
goosebumps.
were choosing
They were choosing that one, the kids,
that
yeah.
one.
Ah, that's really cool.
But
Yeah.
in this case, probably the conclusion will be very strong if you can see the cognitive load reflected on the
Yeah.
size of the.
Yeah, I mean, I don't think you could just, I think you would have to construct a specific type of experiment if you want to make that claim. For example, let's say you have a metaphor, I don't know, the one that I always use, my cat is a princess. And then you ask them a comprehension question afterwards, or of some sorts. Or you have a picture selection task, and you ask them like pick the picture.
Yeah, that's the one.
And then you measure their pupil dilation. If they're picking the wrong one, and there's also no pupil dilation, then you could make that claim. Because you know from their behavior. Yeah. Because you know from your behavior that they're picking the wrong. So you know that they're not making the correct interpretation, right? But if they're picking the correct one, and you see that there's no pupil dilation, which I wouldn't expect, I think this will be weird. I think you couldn't say that they're not processing because they're picking the correct one.
No, it's not
Right.
that they're not processing, but how?
Yeah, exactly.
What are they processing?
Processing it literally, yeah. No, but you see what I mean, right? Like if you would need to have the pupil measurement paired with some behavioral response as well. But yeah, I mean, but that's a really good intuition. Yeah, that's exactly kind of like the thing that you should be thinking about when kind of making a pupilometry experiment. Okay, so one thing that I want to talk about, I want to stress, is that pupil dilation does not mean effort. So this is something that you read in papers sometimes, and I don't think this is fully accurate. You can make it happen. You could say that it's effort, but it requires a careful experimentation. And the reason why I want to say this is based on the findings of this paper that I'm also attaching, but I think other people have made this point as well. And so what I don't know how to pronounce his name, Kiev. What Kiev and Braver did was that they compared the pupil response for trials where people got paid versus trials where people did not get paid. So incentivized versus non-incentivized trials. And they did the so-called AX task. The AX task is kind of one of these very standard psychology experiments where you show a person a cue, and then there's a delay, and then there's a probe where they have to do something, right? And then the idea is that only when they see A, they have to do the X. They have to but if they see something different than the A, they have to do a non-target selection. So basically, it's kind of like so what they did in this experiment is like they would show them first a dollar sign or a green square, and if they saw the dollar sign, it meant that they were going to get paid if they got it right, but not paid if they got it wrong. So they were incentivized to perform better, right? And then they would get feedback afterwards whether they got the bonus or not, right? So then basically, if they saw a dollar sign and they got an A as a cue, they know that they have to select the target response, which is the X. And then what they found was they did this in two speeds, so different types of time response, and they found that speed didn't really matter that much for their pupil response. I mean, it did. There were some differences, but a huge difference was whether they were incentivized or not. So in the trials in which they told they were going to get paid, the pupil dilated a lot more than in the trials where they were told that they're not getting paid. So they conclude that that basically motivation is a strong kind of driver of pupil dilation, probably because the pupil response is an index of how you allocate cognitive resources. If you're getting paid, if you're incentivized, you're probably going to have you're going to allocate more resources to the task because you're like, okay, this is really important. I need to pay a lot of attention to this, which results in more cognitive activity, which will result in more pupil dilation. Notice that this is happening already before, right? But before their probe, right? You see this difference already here. So when they get the cue, they're already like, okay, I'm going to do this. You know? Which is something that you want to consider in the type of experiments you're designing, how you analyze them, and importantly, how you do the baseline correction, which we're going to talk about.
But it's like an arousal, right? I mean, it's like the adrenaline of playing a game or something like
Yeah.
something that it's you're going to get something, an award.
Yeah.
Like the rush.
Yeah. No, absolutely. I mean, but what is that rush? Like, what is the rush of adrenaline? It's also a way of hyper focus, right? So it's like knowing that this is something that I really, really need to do right now, and this is like I'm going to focus more attentional resources to this. Yeah.
Son sistemas atencionales independientes, ¿no?
¿Qué quieres
Si
decir?
estamos pensando en atención selectiva, focalizada o de cualquier otro tipo, es bastante independiente de la arousal. Bueno, no sé si bastante, pero
Sí, o sea, yo no lo vería en términos de arousal, en este caso en particular. But if you want to argue that it is arousal, you can also pair pupil dilation, and I know people who do this, with measurements of what is it called? Like measuring sweat production in the hands. I forget this technique has a name. What is it called? Sí, sí, that's one way of calling it. Yeah. So then you can see whether kind of if you're worried about something being arousal or being attention, you could have additional measurements that could point in one direction or another. And those, the galvanic skin response is actually quite cheap to measure. Right. So that's one thing that you need to consider. Another thing that you need to consider, and why it's hard to say that pupil dilation equals effort, is the so-called fatigue effect. This is a paper by Drew McLaughlin, who I talked about earlier. She ran these series of experiments, and this paper is really good. I'm also adding it to the folder. She ran the same experiment with different types of breaks. So maybe you have heard this, maybe in like an introductory course in experimental psychology, you heard that, you should have breaks for participants after a certain number of blocks. But this is kind of an assumption that is never really tested empirically that much. Is like, what is the break doing? You usually hear things like, you should have a break because otherwise people get tired, right? And what this means for pupil dilation is that your pupillary response will change as a function of the block that you're in. So, I forget what the exact task was in this experiment, but just assume that they're hearing a word and you're measuring how the pupil dilates. In the first block, it dilated a lot more than in the second block, then the third block, and the fourth block. So you have these baseline changes in pupil dilation as the experiment progresses. Yeah. I mean, anxiety. I mean, I think she calls it a fatigue effect, or people have called it a fatigue effect under the assumption that people just get tired after a very long experiments. I'm not sure how scientific this is, in the sense, like, I don't know if they're using some particular measurement of precise measure of fatigue. I don't know if I would call this anxiety. I mean, maybe if it's a small room that they're in and they're getting like claustrophobic or something, I don't know.
Active swimming says makes people nervous.
And so they get more relaxed as the experiment progresses. Maybe, yeah. I don't think so. I think fatigue is a good explanation, but I also don't study fatigue or anxiety, so I don't have any. But I think you wanted to say something.
sí, respecto a la fatiga o
Sí.
al cansancio, en otros experimentos, sobre todo con ERPs,
Mhm.
se ven ciertos componentes asociados al sueño, ¿no? Cierto tipo de ondas, y es cuando,
Cuando están durmiendo, sí, sí,
ajá, o sea,
sí, sí.
cuando
Sí,
es
sí.
una, pues sería ideal hacer un break porque vemos que
Sí, son las alpha waves, ¿no?
La
Que,
velocidad
porque
más.
cuando ve que empiezan a moverse así, es como que esta persona se quedando dormida. Sí, sí, eso es muy chistoso haciendo experimentos de ERP por eso. Pero bueno, what I wanted to say is that so in this paper, McLaughlin et al. Had they ran the experiment 3 times, and they had 3 different types of breaks. One had kinetic breaks, so one had no breaks. One had kinetic breaks, where the participant was told to play with a toy in the break. And then one had social break, where the experimenter talked to the participant. They're like, "Oh, how's it going?" They just talked to something non-related to the experiment, just like a little bit of small talk. And only the one with social breaks significantly reduce the fatigue effect. So if you see these lines, they're a little bit closer to the first one. I don't know if you can see my mouse. Yeah. Whereas the kinetic breaks actually still have quite a big difference, and so does the control one. But even when you reduce them with social breaks, the effect's still there. So your pupil size of the experiments, which is also a reason why you want to have a way of accounting for this, for the fact that from a trial to a trial, the participants' pupil will dilate differently, which is one of the reasons why we're going to have baseline corrections, which I'm going to talk about in a bit. Another conclusion, besides the fact that you need baseline corrections, is it is ideal to have pupillometry experiments that are as short as possible. Remember how I said that the effects are usually quite big? So you can allow yourself to have a lower number of items. Of course, you should do a power analysis to actually see what is the predictive effect that you want to have, and you know this is the correct way of doing it. But you usually find bigger effects, so you can probably have a smaller number of items. And the effects that you find are also consistent from item to item, which is a huge advantage to other, in comparison to other neurological methods. For example, if you use EEG, you usually have to have hundreds and hundreds of trials because the data is incredibly noisy. With this, you get actually data that is not that noisy. So you can get away with an experiment with only like 16 trials. And then you also avoid this kind of fatigue effect, if that makes sense. Okay. Okay, so far, what are we seeing? Cognitive pupillometry is the measurement of pupil size changes over time to investigate cognitive processes. It is used to study processes related to cognitive load, such as attention, mental effort, working memory, among others. A whole range of cognitive phenomena has been investigated with pupillometry. It's typically measured using an eye tracker, but you can also take pictures of people's eyes, you know, if you want to spend several weeks manually doing it. The pupil responds to, and this is going to be really important to consider. One, changes in illuminance. This is the biggest driver of pupil size change. Changes in visual attention, right? If they're looking here, if they're looking there, the measurement will be different. If they're focusing in on something close by or something far away, the pupil size will change, right? This is what we saw earlier. Baseline differences in engagement. If people are getting paid or not, there will be differences in how their pupil dilate, so how they're allocating mental resources. If you've been tracking their eyes for an hour and a half, they're going to get fatigued and their pupil will dilate differently. So there's these changes throughout the course of an experiment. Changes in cognitive processes, which is the one that we're probably mostly interested in, right? If they process object relative clauses differently to subject relative clauses, that's probably what we're actually interested in, right? The cognitive processes. So then we're left with this kind of problem, which is we want to create a pupillometry experiment, but actually the pupil responds to pretty much fucking everything. So how are we going to do this, right? This is a huge problem, and this is actually the biggest problem to solve when it comes to designing a pupillometry experiment. And the answer is twofold, namely, with some careful experimental design and with some good data pre-processing. So if you have these two things in mind, it will actually be a lot easier than doing an eye tracking experiment. And we're going to talk about that throughout the day and also tomorrow, why I think this is easier. Right, so the first thing you want to do is you want to control and prevent problems when you design a pupillometry experiment. Things that you need to look out for: the pupil light reflex, right? You have to control lighting conditions. This is the biggest, most important thing that you need to do. If you don't do this, you're really fucked. Like, you need to make sure that the lighting conditions are identical from participant to participant. You can do this using you can buy on Amazon an illuminance measure that just measures in lux how much illuminance you have in a room, and you just maintain it at a constant level. Or if you have a lab where that doesn't have any windows and you have the same lights, and you know that's the only light that you turn on and there's no other source of light, you can do it like that. As long as you know that this is the same for all participants at every moment of the day. This might sound kind of banal, but obviously there's light changes throughout the day. So if you have windows in your lab, and you're testing one participant at 8 in the morning and the other participant at noon and the other participant at 5 p.m., you're going to have changes in the pupillation as a function only of the time of day. You don't want to have this, right? You don't want this to happen. So you have control lighting conditions. Importantly, if you remember, I showed you this graph of Sebastian Matote's pupil dilation as a function of the type of light that he was seeing. So it's not just light or no light, but different sources of light will produce different pupil light responses. If you're showing people a computer screen, different sources of light mean different colors, right? So a blue color will make us, I can show you the graph again. Showing people the color blue will be very different than showing people something with the color red, right? So you have to, where was that here? Yes, you have to try to match your visual stimuli between conditions. Does this make sense to you guys? Yeah?
Very, big question.
Pero la voy a molestar tantito antes, es que no se escuchan las preguntas en YouTube, entonces cuando hagan preguntas le voy a pasar nada más.
Se supone que no estamos en el the light coming from the computer is usually, it is said that it's blue, right? Which will be an example of red light, or are we talking about something in vitro?
I'm talking quite literally.
Oh.
Like if you show a picture of something that is red, the way that will hit your eye is differently. So the graph that I just showed you, where is it again? This graph is literally a graph of Sebastian Matote looking at a red square on his computer versus a blue square on his computer. So yeah, exactly. So
It's literal.
it's literal, yeah. I'm being quite literal, yeah. Yeah, I don't know anything about like the actual like blue light. I don't know anything about this. Where was I? Yeah. So what I mean with match visual stimuli between conditions, maybe this will probably not be a problem for you guys. It's not really a problem for me because when you're studying language, you can just show people an X in the middle and you have them listen to something, right? That's what we care about. We care about language. So you show they hear something and then that's what changes. So you're good if you do that. But people who do cognitive experiments where you're interested in like different pictures, they need to do really complicated things to make sure that they're matched. So you can pass them through like a complicated algorithm that will check that the pixel distribution is the same. And then you have to have a specific baseline correction so that you're accounting for this. But I mean, don't make your life hard. Make the visual stimuli between conditions identical. Just show people an X in the middle and make sure that you create a clever experiment where you care about is only played through speakers or through headphones. Does that make sense? Yeah. You have a question?
Okay.
Or, for example, the pictures that Merari showed that are all black and white, even though they have different levels of complexity, do they work?
Not really, no. I mean, you would have to check them with an algorithm because like then the number of lines of black lines, this will also influence the light that is the proportion of black versus the proportion of white. This will change, right? I mean, yeah, I really wouldn't mess with this. Yeah, I know that people do this and there are complex algorithms that you can use to kind of account for this, but you're just making your life a lot harder. Yeah.
Okay.
So I would suggest making really simple experiments where people hear a sentence and the only thing that they see is just a cross in the middle of the screen. That would be my advice. Also because I'm lazy, so this is the easiest way of doing this. Right. Even if you try your best to make the best possible experiment, you still will have to do some correcting after the fact. And this is something that you absolutely have to do. Those of you who maybe know something about EEG experiments know that this is also something that is done here, which is in the pre-processing, you correct for baseline differences in lighting. So let's say that there's a difference in lighting for participant A versus participant B. So when you do a baseline correction, where you take maybe the first 100 milliseconds before the trial is presented in participant B, and you subtract what you actually care about, so the time of stimulus presentation, you subtract those the pupil diameter from the baseline, from that, and then you get a measurement of the change relative to the baseline for that specific participant. So you're kind of subtracting away any possible impact of light. So does that make sense to everyone? So basically, imagine that the light conditions for participant A are here, and for participant B are here, but what you care about is the relative change for one here and the other one here. So you get that relative change just by looking at by doing a baseline correction. It's really, really important to do this, and we're gonna show that. We're gonna look at that tomorrow. Right. So that's how you account for the pupil light reflex.
So we have a question.
Yes.
You talk about the difference of time of the relation between warm light, well, with the red light and blue light.
Yeah.
So in the room, is it better to have neutral light, warm light,
It's better to have
like the
If-
one and
yeah. It's better.
yeah.
It's important to have kind of as neutral as possible. So you don't want to have complete obscurity.
Mhm.
Complete obscurity is bad because it will force participants' pupils to dilate a lot.
Mhm.
And there is a natural upper bound. It's not like the people will dilate infinitely, right? So if your baseline is already at here, you might find a null effect but it might actually be a ceiling effect. So it might be that the people cannot dilate more because it's already dilated at a very high level. So you actually want to have people's pupils be quite small. It's important also that you consider computers emit light, right? And if you have have you ever had the situation where you're in a dark room and your computer screen is very bright?
Yeah.
This hurts your eyes, right? You want to avoid this. You want to have a room that has roughly the same lighting as the computer screen. So you would want to have basically a somewhat dimly lit room and reduce the brightness of the screen and match them. Yeah, I forget the exact number of lux, but in the Matot paper that I'm sending you tomorrow, the 2022 one, he discusses precise numbers of lux that you could use that serve as a guideline. So that's how I've done it in the past. So and how you would report it in a paper, basically. Yeah, that's a really good question. Right. So the other thing that I talked about, the pupil near response, right? Basically, the pupil will change as a function of whether they're looking close or far. This is pretty easy, right? You create a single central viewing point for participants. So you want to reduce people's eye movements. You want to keep people looking at one spot, which is why I would suggest also that you just draw something in the middle. I normally have a cross, right? But you can have a circle, and you tell people to only look at that. Of course, this could be also somewhat cognitively straining, which is why you want to have ideally shorter experiments so that it's not too annoying for people. If you have a single spot where they're looking at, it makes everything a lot easier because you get rid of the pupil near response because they're not looking closer or further away, and you also control for these saccadic eye movements, basically because they're not moving their eyes around. It also makes the actual programming of the experiment a lot easier because you don't have to have multiple regions of interest, like in an eye tracking experiment that you have to kind of account for. You just have a single region of interest in the middle, and you only look at the eye movements that fall within that region, and you exclude everything else, and you have like kind of like a consistent spot that they're looking at all the time. Does that make sense? Right. You also want to avoid manual tasks. This is really, really important. Let's say you're interested in the participants hear a sentence and you want them to say whether the sentence is true or false, right? Like a typical sentence verification test. You're gonna have to be clever about this because you don't want people looking down at their hands, which is something that people do all the time. Because when they look down, their pupils are going to constrict, right? Or depending on how far away, you're eliciting a pupil near response by doing this. What you want to do is you want to have the critical part of a trial, then have like a second or two, and then have them do some sort of task. So you want to disentangle the pupil record from any other manual task that they might do. Which is also great because since this is not a controlled movement, pupil responses are completely involuntary, you don't need to have them do any task at all. They just passive listening. You just have them listen to something, and their pupils will dilate, like, because they're processing it. You just need to kind of figure out a way that you can make sure that they are processing it and not just ignoring it. So what I normally do in the experiment that we're going to look at tomorrow is I tell them that at the end of the experiment, they're going to have a questionnaire evaluating how much they paid attention to the experiment. And so then throughout the experiment, they're not doing anything, they're just listening. And then at the end of the experiment, there's this questionnaire that they fill out. And if they get most of them wrong, I eliminate them from the experiment, basically. But you can do different things, right? Okay. Avoid manual tasks, right? You don't want them to be looking at anything else. You don't want them to be doing anything else. And this is going to be critical. This is what you're going to be spending most of your time doing when you're doing this kind of pre-processing, is you're going to have to correct for eye tracker artifacts. So when people move their eyes, you're going to get, unfortunately, sometimes you will get an NA, like a missing value, if there's no pupil diameter being tracked. Most of the times you're going to get faulty measurements. Faulty measurements are a lot worse than missing values, because if you're doing regression modeling can deal with missing values. But if you have faulty values, it's going to distort your results. So what you want to do is basically, when you're in, if you are in this constellation right here, you want to figure out ways in which you can get rid of those eye movements. So you want to identify them in the data set and remove them. The real headache, or I mean, this is actually not going to be that important, especially if you design the experiment where they look in the middle. The real thing that you have to pay attention to is blinking. So what happens when you blink is that your eye gets smaller and smaller, right? So your pupil size, or the way that the camera will measure your pupil size, is suddenly there's a huge drop in pupil diameter because you're closing your eyes. Then there'll be a bunch of missing values, right? Because then there's no pupil. And then people open them again, and so this starts getting bigger and bigger and bigger again. Additionally, when you close your eyes, because it's dark, your pupil dilates, right? So what you basically want to do is you want to identify blinks, and you want to remove basically 100 milliseconds before and after every blink. So you're going to have a gap. And then what people normally do also is what is called an interpolation of the data. This basically just means, let's say, can I just draw on this? Let's say you have, right, here you go. Let's say you have like the pupil record going like this. Am I doing this correctly? Okay. Okay. Let's say you have your pupil diameter kind of like going like this, growing, and then suddenly you blink, and then what you're going to have is something like this. And then it'll continue like this, right? So you want to get rid of this, right? So you want to do like you go to R and you do all these fancy things, and you're like, oh, okay, oh, fuck, I didn't want to delete the whole thing. How do I, man? Why am I so incompetent? Okay, here we go. Okay, so you have something like this, and then it keeps going, and then you want to. How do I use an eraser? Can I? Is it possible to have a?
Yeah.
But if I do it, it'll just erase the whole thing. Oh man. Okay. Anyway. Is it this one?
Change the color to white.
Ah, very smart. That's why they pay you the big bucks. Okay. Here we go. So you wanna get rid of this thing, right? Oh, this is so cumbersome. Okay. All right. So you want to get rid of this, right? What the hell? Okay. Pretend it was deleted. Okay. Jesus Christ. Okay. And then after this is gone, you're left with a bunch of missing values, right? And then you want to fill them in. You would fill them in by doing linear interpolation, which just basically creates a line from one point to the other. Or you could do a spline, or you could do different types of interpolation. So you could, for example, assume that there's a linear continuation, or that it goes a bit like this, so it's a little bit curved. Normally,
Aren't you tampering with the data
yes.
by doing that because you are assuming that actually the linking the line
Yeah.
went that way, and what if it, I mean,
Yeah, that's a really,
naturalistically without the link, it could have gone.
that is a good question. We assume that because the pupil dilation is slow, right? It takes about a second to peak. If you're looking at, let's say this is a time range of 500 milliseconds, it's very, very, very unlikely. I would even say impossible that your pupil will be like that you missed that. It would actually, if the person hadn't blinked, it would have actually been it would have actually been like what the hell's going on? Yeah. That it would have actually been
Okay.
you assume that, especially if you have like this and the stimulus has not peaked yet, so it's for a second, you would assume that it's just going to keep growing, or it's going to keep in the same direction, or if it's going down, you would assume that it's going to keep going down in the same direction now.
So that linking line will really affect the.
It doesn't really affect it, no. No.
Okay.
No. Matoed 2022 also talks about, he cites a lot of papers that he argues that, yeah, that the type of interpolation that you do should not really matter. So whether you do linear or spline or cubic, the problem is that if you have a lot of blinks in one trial, after a certain threshold, you should just delete, you should just get rid of the participant. If the person is blinking all the time, you're like, yeah, you should get rid of that data set, or that data point. But if you have a lot of blinks and you don't do any interpolation, this will affect your power. Like, you just have a lot of missing values. So interpolation is actually quite handy, and is, I would say, Matoed recommends it, and other people recommend it as well. And yeah, we will see tomorrow what kind of effect it has.
Okay.
Yeah.
Thank you.
Okay. Right. Okay, wait. All right. Where was I? We did this. Correct for eye tracker artifacts. So blinking is the biggest one, right? There's you will find sometimes other artifacts that we're gonna see how we delete them, because they could influence. There's fancy ways to detect artifacts. Like if there's really strange pupil dilation patterns, you can automatically remove them. You can also do a visual inspection and see whether you have dilation values that are physically implausible, like biologically implausible. So you're like, okay, this must be a mistake from the eye tracker. Engagement of participants. This will affect your pupil size, right? My recommendation is always make experiments as easy and as engaging as possible. This is my recommendation for when I teach intro to psycholinguistics or experimental methods. Always make just very short, very easy experiments. Don't make your life hard. I know this is important to tell linguists, because I feel like linguists, we tend to make really complicated experiments. Like linguists will make experiments that have like 15 conditions, and it is just like a giant questionnaire, and you're like, oh my god. What was Juan telling Carlos? I don't know. I think this is something that we like to do because we care about things that are really fine-grained, right? So we want to have all these conditions. It's important for what we do, but it's a trade-off. We need to keep people engaged. Keep experiments short, and again, also correct for baseline differences for possible fatigue effects. So within a trial, if a participant is fatigued in trial 25, then we subtract the whatever effect we find, or whatever pupil dilation happens in it, in the same trial, so that we're kind of accounting for this fatigue effect, if that makes sense. Are we all on board? Yeah. Okay.
Sorry.
Yes.
Well, we see that with this effect, the dilation changes, but does it dilate more, or does it contract?
That is a really good question. So when I talked about at the beginning about these two muscles, and they're doing two different things, the reason why I stress this so much is because what we care about is the dilation, not the contraction, right? because the dilation is the one that is associated with cognitive activity. The contraction is mostly associated with like wanting to return to with homeostasis. So they're controlled by different autonomic nervous systems. So yeah, we want to track basically the release of neuroepinephrine in the brain. Yeah, but I mean, I think it's fair to just talk in shorthand of changes in pupil diameter, right? I don't know if we can be always like 100% sure of which of the muscles is being used. I would say that that's probably fine for what we're doing. Right, where were we? Engagement of participants, make it easy, correct for baseline. Pupillary response time. As I said, it takes about a second to peak, right? You need to like account for the time that, you know, the flow of epinephrine in the brain, and it takes about a second to peak after onset stimulus. So what you want to do is you want to add plenty of buffer time before and after any critical period. So you want to give people basically time for the pupil to return to baseline. So this is an example of what, you know, a controlled experiment would look like. You would normally have some form of baseline period. Let's say you have, you know, 3 seconds where you just see a cross, right? And then you have a stimulus period. I wrote 2,500 milliseconds because that's the duration of the stimulus that I'm going to show you in my experiment tomorrow. And in here you replace some sort of critical sentence, right? And then after they hear the sentence, there's like you can have a slight delay. This could be 2 seconds or 3 seconds, right? And then maybe you have some sort of task that they have to do. And then what you measure is the data from here, right? So what you would want to do is that you would take the time from the stimulus period and you would correct it using the baseline that you measure in this period. Usually you would take like maybe the last 300 or 200 milliseconds from the baseline period, or like the 300 milliseconds right before the stimulus period, and you would do a baseline correction. As I said, so Matot and nowadays people favor the subtractive baseline corrections, because another form of doing a baseline correction is the divisive baseline correction. So you take, you know, stimulus that pupil diameter minus baseline divided by the baseline. But Matot argues that this inflates your false positive rate. You basically are more likely to find a significant effect that's not there. So subtractive baseline correction is better. Okay, I'm almost done. I just wanted to show you an experiment, a pupillometry experiment that is not about language, but it's kind of cool. And it's by colleagues of mine at the University of Oslo. So you can kind of see what a good experiment would look like that is not necessarily a language one, that does involve pictures. So what Langens and Sulevet studied was what they called the imaginary pupillary light reflex. So they showed people triangles of different colors, and then they asked the people in a period where there was nothing on the screen, they asked people to imagine or to think about the triangle that they saw, and then they measured their pupil dilation during that moment where they were imagining, right? So then you have a baseline of like, this is 2 trials, this is two critical trials. So there's a baseline that they use for the subtraction of a second. Then there's a triangle that they see. Then there's a dark that goes completely dark. They use this to measure, so this is a kind of like a control condition. Then there's a period of, and then in here the pupil returns to some sort of baseline after having seen this triangle. So you're doing all these things to kind of make sure that the pupil kind of goes back to kind of some sort of normal state. And then there's the moment where they have to imagine it. And then it goes back to the baseline of 1 second so that it returns back to some sort of baseline. And then you have the next trial. So you're doing all these things to make sure that what you're interested in measuring is actually what you're measuring, right? And then here's the results that they found. So they manipulated the color of the triangle. That's the only thing they manipulated. So whether it was lighter or darker. And here's the results. So what you see here are the hues of the triangle. So these are the really bright ones, and these are the really dark ones. So they had all these different ones. What you see here is the pupillary change from when so the diameter of the pupil or the pupil size when they're looking at the black dot. So this is kind of to assert that there was a baseline across all of the colors. So no matter what color of a triangle they saw, their pupil dilated roughly the same. And then the two interesting ones are the perception. So this is the blue line. This is when they actually see a triangle. So they're actually seeing something. Their pupil dilates more. Their pupil is less dilated when they see brighter triangles. That's to be expected. That is the light reflex. So things that are brighter make your pupil smaller. That's the blue line. But importantly, the green line is when they were imagining it. So they're not actually seeing anything, but their pupil is changing in size as a function of the color that they're imagining, which is pretty crazy. I mean, it's basically like shows the power of pupilometry. You basically like willing your the world by sheer like the force of your mental representations, which is awesome. But anyway, so that was pretty much it. Thank you. And I don't know, do you have any questions about this? Anything you want to talk about? I hope it wasn't too much information. Are there any questions on YouTube?
Just one question. Is it important to know what's the dominant type or
No.
no?
As far as I know, we assume that the pupils of both eyes dilate and constrict in the same way.
Okay.
Yeah.
¿Alguna otra pregunta? ¿Comentario?
Pregunta, comentario, duda, crítica, insultos, se recibe todo.
¿Importa si el participante está usando lentes con protección para la luz azul?
Probablemente sí, o sea, sí, no, o sea, los participantes no deberían usar ningún tipo de gafas. Se pueden usar lentes de contacto, o sea, la mayoría de cámaras funciona bien con lentes de contacto suaves, de los que son, creo que ya nadie usa los lentes de contacto duros, los que la gente se podía dejar como una semana entera en los ojos. Los suaves no hay problema, pero no se pueden usar gafas por lo general, porque cambian, distorsionan mucho la medida de la pupila. Pues, o sea, es difícil de decir como sí o no, porque a veces se puede, o sea, a veces uno trata de calibrar a un participante y se ve que funciona, pero pues como la luz pega diferente, se refleja diferente en las gafas, es un riesgo un poco. O sea,
Y otra pregunta, cuando haces estudios con eye tracking, sí hay forma de calibrar y de ver que está funcionando bien, digamos, o sea, que está calibrado, ¿no? En pupilometría, ¿hay alguna manera de saber que está funcionando bien?
pues depende del tipo de eye tracker que estés usando. O sea, si el experimento lo haces con uno de estos eye links, el proceso es el mismo de calibración que cuando es un experimento de eye tracker. O sea, salen los 9 punticos, o sea, lo puedes hacer si quieres exactamente igual. O sea, no necesitas calibrar los ojos al mismo nivel que un experimento de eye tracking porque no hay movimientos. Es más, tú quieres que no se muevan los ojos. Entonces, realmente no te importa si lo están midiendo perfectamente cuando está en esa parte de la pantalla, porque idealmente nunca van a ver esa parte de la pantalla. Y la calibración por lo general tiene que ver con el reflejo de la luz en la córnea, el primer reflejo de la luz en la córnea, que eso que eso es bastante difícil como de obtener perfectamente, pero tienes que calibrar todo esto, mientras que por lo general los eye trackers son mejores con el diámetro de la pupila. Pero en sí es el mismo proceso que con un eye tracker, el términos de calibración. Hay eye trackers que no necesitan ser calibrados. Las gafas que les mostré, las Neon Labs, por lo general tienen un proceso de autocalibración. Bueno, porque la cámara también está al lado del ojo, entonces no tiene esos problemas de la distancia del ojo a la cámara. Y bueno, no sé cómo funciona el TOEIC que tienen ustedes. Tiene un proceso de calibración normal, ¿no?
Sí.
¿Alguna otra pregunta? ¿Hay estudios con toddlers de pupilometría?
Sí, creo que sí. Es difícil como, igual que con eye tracking, porque tienes que poner el tracker en la cara, pero sí se puede hacer. O sea, es bastante Pues, o sea, de cierta manera está mejor que usar eye tracker con toddlers, porque pues te dice algo más como directo, pero así como off the top of my head no se me ocurre ninguno, pero podría buscarlos para mañana, no sé, alguno.
De aquí de la universidad, de la Facultad de Psicología del Laboratorio de Lingüística Experimental.
Usando bibliometría.
Sí.
Ah, está bien.
Sí.
Gracias. Eso.
Hay una pregunta en YouTube. Undergoing a medical treatment can affect the diameter of the pupil. Would this be a reason to turn down a possible participant?
Absolutely, yes. Yeah. I mean, yeah, if you have a situation where the changes of your pupil are affected by medical treatment, you should probably not participate in an experiment, right?
Like eye correction surgery.
I mean, I don't know what medical procedure they're talking about specifically, but if it's a medical procedure that affects how your pupil dilates, you should probably not participate in an experiment.
So that should be a question that you.
Yeah.
That
Should be a question that
Yes.
you as experimenter.
Absolutely, yeah.
should ask.
Similarly to with eye tracking, you should have normal or corrected to normal eyesight, is what you would ask for. Yeah. If someone has like I don't know what the correct term for this is, so I'm sorry if this is not a politically correct word, but if you have a lazy eye, like you should also not participate in an eye tracking experiment. Estrabismo, sí. I don't know what the correct word is in English. I'm sorry.
¿Alguna otra pregunta aquí en el auditorio o en YouTube? Bueno, yo tengo una pregunta. Hablando de los neoclases, entonces, ¿cómo es ese procedimiento si estamos considerando que la parte de los colores y pues todo esto afecta a la diferente luz? Entonces, en este sentido, ¿cómo puede ser una ventaja si realmente tienes que controlar todas estas variables de luz y de colores?
Claro, pues es una ventaja porque no tienes que primero usar la mentonera, o sea, donde no tienen que estar como sentados fijos, o sea, no hay que hacer ningún tipo de fijación y no hay que ser estricto sobre la distancia necesariamente a la pantalla. O sea, en cierta manera sí, porque tú quieres que se mantengan constantes, pero es un poco más laxo. Y si logras controlar el cuarto, el lugar donde están haciendo el experimento, puedes tener a las personas, digamos, dos personas sentadas una al lado de la otra, hablando, mirando de pronto ambos al mismo sitio, pero mucho más cercano a a una interacción naturalista, como, o sea, no es 100% naturalista porque igual no puedes, o sea, es complicado tener dos personas con las gafas hablando la una con la otra, porque los ojos se les están moviendo y nos tendemos como a indexar como el movimiento de los oculares de nuestros interlocutores, entonces eso es como complejo, pero puedes como tener ciertos trucos y ayudas para hacerlo aún más naturalista que si tienes pues una persona sentada al frente de un computador que no se puede mover.
Okay, sí.
Pero sí, no soluciona todos los problemas, sí, 100% igual, o sea, todavía falta como superar esa frontera.
Gracias. ¿Alguna otra pregunta, duda, comentario? Bueno, con esto cerramos el día de hoy, el tercer día del primer encuentro del Lingüística Experimental. Nos esperamos mañana a partir de las 10. Muchas gracias.
Muchas gracias.